Okay, we're continuing on with Module 7. We're going to talk a little bit about gravity. Gravity has been pondered by scientists for as long as there have been scientists to ponder about it. The first time we really hear about it was with Johann Kepler back in the late 1500s, early 1600s. He spent a lot of time studying the movement of the stars and the planets and thinking about what held everything together. And his work was used by Newton to come up with the law of universal gravitation. And basically what the law of universal gravitation says is that everything exerts a force of gravity on everything else. So while you know that the Earth exerts gravity on you, as we've discussed before, you are also exerting some gravity onto the Earth. And we know that according to Newton's first law, according to Newton's second law, force equals mass times acceleration. So if you are exerting a force on the Earth, that force will be a certain thing, and your mass is going to be very, very small compared to the Earth, so your acceleration is going to be much greater. But we said that you are also exerting a force on the Earth, that same force, and the mass of the Earth is just so much, much greater that the acceleration it experiences is infinitesimal. We can't even get a gauge on what it is. So the Earth is accelerating toward you, and the same way you're accelerating toward the Earth, but due to the differences in the masses, that acceleration is completely opposite. But the forces remain the same, equal and opposite, Newton's third law. Later, Einstein also had the general theory of relativity. Gravity is still not completely understood by scientists today, and so there's a lot of time spent on studying space and gravity and how it all works together. But Einstein has the general theory of relativity that any mass will deform space and time and pull other things toward it, which is basically just saying that gravity is working. So Kepler had come up with 3 laws about the planets, and Newton used those in order to come up with his universal theory, his theory of universal gravitation. And so basically what he was saying is, if I was on the Earth and I used a slingshot to send something, I could get it up in the air for a little while, but it's eventually going to fall back to Earth. And if I use a little more force, I can get it to travel farther, but still the Earth's gravity is going to pull it in. So if I keep getting stronger and stronger slingshots, I can get it farther and farther, but it's still always going to fall to Earth. Until I can accelerate it at such a speed that it starts to orbit the Earth. And so a lot of times people get confused and say there's no gravity in space. That is not true. There is gravity, but things like the satellites and the space shuttle and stuff are traveling at such a high rate of speed that they're having circular motion. They're basically in free fall, but gravity is still affecting them. No matter how far you get from the Earth, you're still going to experience gravity. And it does change a little bit. As we know, distance affects the rate of gravity. On Earth, we experience an acceleration of gravity of 9.81 meters per second squared. Out in the space shuttle, a couple hundred miles away, it's still close to 9. It's probably 8.8, 8.9 meters per second squared. So you have to get very, very far away for the effects of the Earth's gravity not to be working on you. So what is the formula for the universal law of gravitation? Is that the force of gravity is going to be equal. Now remember, force of gravity is different than acceleration of gravity. The acceleration of gravity is known as little g, and we know that's 9.81 meters per second squared on the Earth. But we're talking about the force of gravity, And the force of gravity was found by Newton to be this gravitational constant. And the gravitational constant, big G, is a very, very small number, 6.67 times 10 to the negative 11th, and it has some crazy units, Newton meters squared per kilogram squared, basically to help work all this out. So the force of gravity is equal to the universal gravitation constant times the mass of one object and the mass of a second object divided by their distance squared. So when we're talking about the distance of the two masses, the radius, okay, we're talking about from the center of one object. So if we're talking about things on the Earth, we're talking about the center of the Earth to the center of the object on the Earth, or the satellite out in there, the center of the satellite orbiting. So if you're given information about the distance, be sure that you're calculating it from the center of the object to the center of the other object, not a lot of times they'll talk about the distance between two planets, and it's still talking about the distance from the center to the center. So if you're given a distance from the surfaces of the planets, you have to be sure to add the distance to the center of each planet to use this formula. Okay, so let's use. We're going to do, we'll look at on your own 7.6. Oh, 7.5, which talks about the gravitational force. So the gravitational force between the moon and the Earth. They give us the mass of the Earth, which is 5.98. We're going to be dealing with some big numbers here, obviously. Mass of the Earth. And the mass of the moon. And they give us the radius of the Earth, 6.38 times 10 to the 6 meters. And the radius of the moon, 1.74 times 10 to the 6 meters. And it says the distance between the surface of the Earth and the surface of the moon. So just like I was explaining before, okay, they're giving us this distance. I'm going to put that as D for right now. Between is 3.76 meters. Yeah, times 10 to the 8th meters. And we know that the constant is 6.67 times 10 to the negative 11. So what do we do with this information? Well, first we have to figure out what R is, because as I said before, they gave us the distance here. They did not give us the distance to the center of each object in the total. They did, however, give us the radius of the Earth and the moon, so we can add them together to figure out what our R is. So that's simply the radius of the Earth plus the radius of the moon plus the distance between the planets. So we know that R is going to be equal to 3.84 times 10 to the 8th meters. I just added those three numbers together to get us our R, so that we could then use our universal gravitation formula. And so now it's a straight kind of plug and chug information. We know that we're trying to calculate the force of gravity, and we know that big G, 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. times the mass of the Earth times the mass of the Moon, and divided by the radius that we calculated, 3.84 times 10 to the 8th meters. And so we plug all that in, and we get 1.99 times 10 to the 20th, and the units will be, hopefully, our kilograms squared cancels out, and this is squared, so our meters squared cancel out, and we are left with newtons, which is good because we are looking for a force. Force is always in newtons. Okay, so again, earlier we had talked about frequency and periods and in circular motion, and so On Your Own 7.6 deals with that one, and so we'll do that. On Your Own 7.6 says a child's train moves on a circular track if the train has a constant speed of 1.8 meters per second and the radius of the circular track is 0.81 meters. What is the period and frequency? So we want two things. We want to know the frequency, and we want to know the period of the train. So we know that we have the velocity, we have the radius, we want to know its rate, and we need to know the circumference. And so we can remember that distance equals rate times time, and distance also equals the circumference, which is 2 pi r. So we can set those two things equal to each other. We know that 2 pi r is going to be 3.14 times the radius, 0.81 meters, and that will be equal to the velocity times time. Rate times time, velocity is rate, and we don't know the time. So that's what we're trying to solve for. So doing the math, we put that together and we come up with 2.8 seconds equals our period. So that's the answer to that question. And we know that frequency equals 1 over time, and so 1 over 2.8 seconds equals 0.36 hertz, which is our frequency. It goes around the track 0.36 times every second. Okay. So hopefully this is a little bit just an introduction into circular motion. We'll go more into this before we go on our field trip to Hershey Park, where we'll talk about the forces affecting you during roller coasters and on rides where you get stuck along the side. So we'll be doing a little bit more about this circular motion later in the year. The rest of the chapter, he is using the universal gravitational formula and rate and time to figure things out. So hopefully that all makes sense to you, and I'm going to do another video where I work on some of the practice problems. So